So, good morning to all of you. We were discussing second law of thermodynamics or second law efficiency of power cycle analysis. In the previous class we discussed this what is the difference between first law and second law here in terms of flow, steady flow processes. This for steady flow processes you can see that this is a first law equation and this is a second law equation, and here the heat rejected to the surroundings is treated as a negative, and entropy generation is this delta total should be greater than or equal to 0, and if you eliminate those and substitute in terms of work here, these equations are then this heat terms here relative to the entropy and dead states are given. This is the actual work done during the process, which is also useful work since the steady flow devices have to be fixed with boundaries and do not involve any work by the against the surroundings, and this can be written as same with this potential enthalpy, kinetic energy, potential energy, and the energy which is lost to the due to dead state kind of thing. So, reversible work can be obtained by entropy generation equal to 0. So, in the here this entropy generation becomes 0. So, therefore, now you can rewrite this equation and for multiple streams, but if you have a single stream, this is the reversible work, this is a reversible work which is written in terms of enthalpy and the heat, and then you have kinetic energy and potential energy, and you can look at this reversible work is the work which is maximum available mechanical power, and you can also write this in terms of their PdV work, internal energy work, and so on. This is written in terms of time if it is a transient condition, and then this is accumulation of non flow exergy, and this exergy transfer via heat transfer, because this is defined with reversible heat engine performance, that the highest performance is considered here, and then this is intake flow energy via mass flow, but that is enthalpy, and the heat is removed, and this is the out one. So, this is in and this is out, and these are written here, but now if you replace with the initial state by existing state, you can rewrite this here. I think something is gone. You can see that it is written in terms of availability, which is already defined as a standard format here. The enthalpy is defined at any state. Enthalpy is defined with respect to dead state like H naught, S naught, and so on. So, the reversible work for steady flow process is given by change in availability here, change in availability at specific availability at inlet minus outlet, that is given by this equation. So, therefore, now this is a reversible work, but there is a irreversibility associated with the steady flow process. The reversibility is given by reversible work minus useful work. So, which is given by that is the entropy generation here. So, therefore, if you can conveniently adapt this to vapor cycles like Rankine cycle or so, and irreversibility of steady flow system which in which the heat is exchanged with the reservoir at temperature Tr, and which can also be expressed as this. So, this is the irreversibility when there is a steady flow thing. This can be expanded into this at the entry, exit, and if there are multiple streams, and then you are also writing with Qr by T, that is another this one. So, irreversibility for steady flow, if you consider again this is a simplification of this, because if you consider single flow, if there are multiple flows you have to submit, then if it is a single flow it is conveniently written in this fashion. Again availability is the same as I think this is a repetition of that availability of a process, which you can see the previous one also same, it is a repeated. So, now we look at a case study where I think you have received some documents from him. We will look at one case study, it is a coal based power plant. We are finding exergy and energy balance for this power plant, and the temperature and pressure are given here. There are 3 to 4 total 4 power plant configurations have been considered. One is the subcritical, whose pressure and temperatures are given here, supercritical, pressures temperatures are given here, advanced supercritical, pressures temperatures are given here, and ultra supercritical power plants. If you look at most of these, you see the pressures are greater than advanced supercritical, pressure than 300 greater than 300 bar, and temperatures around 600 degrees Celsius. So, if you look at subcritical to ultra supercritical, only there is a variation of 60 degrees Celsius. Earlier I mentioned that temperature is a major, you cannot increase too much because the meteorological parameters plays an important. Pressure you can increase by increasing the thickness of the tube, but you cannot increase the temperature because it may melt, the tubes may melt. So, therefore, here in fact this is the general information here, energy exergy balance performed 3 plants each of subcritical, supercritical and ultra supercritical steam conditions respectively to investigate the efficiencies and heat losses, and most recent plants in India operates about 37.5% grasp efficiency and uses subcritical parameters, but the 500 megawatt subcritical power plant with this is in India with 166.7 bar and 537 degrees Celsius. These are the parameters which consider for this capacity. So, therefore, if you look at the configurations how in detail, whatever papers he has sent, they are based on these concepts only. So, 500 megawatt pulverized coal, it is a pulverized coal combustor, it is and it is based on subcritical stream parameters run by NTPC India, and stream parameters are this 166.7 bar and 537 degrees Celsius, that is a 2 stage. This is the first stage is 537 inlet to the HP turbine, high pressure turbine is 537, LP turbine is 303. So, another important 660 megawatts supercritical conditions, and these are there is a difference in parameters. You can see the temperatures are almost same here. This is supercritical where you have next inlet to the next turbine is 565 degrees Celsius. And another concept, this is so far in India there is no ultra supercritical power plant, but this is considered as a conceptual 430 megawatts, and the pressures you can see here 350 bar, which is much higher than the supercritical, and 700 degrees Celsius and 720 degrees. This is a conceptual, as I mentioned, though the practically the temperatures are 600 degrees Celsius only. And this is the cycle, you can see that it is a complex cycle, which you can see here the air comes from this and air preheats and goes into the combustion chamber, and coal come here, and the flue gases pass through this and then goes out here. And in the process you have a evaporator, superheater, reheater, economizer, air preheater, and finally it goes, this is a induced draft fan. And in this process you can see how complex here there are 1, 2, 3, 4, 5, 6, 7 feed water heaters, and 7 plus 1 deaerator, 8 feed water heater system. In the feed water pump see pump, auxiliary pump generally is driven by the electricity, but you have seen this in a general Rankine cycle, simple Rankine cycle. What happens is you have a pump here. This pump part is actually it is about 5 to 8% parasitic power, whatever turbine developed. When you write efficiency, the W net by heat supplied, but this W net means turbine work minus pump work. So, but what happens is if you drive pump by electrical energy, it will be a different thing, because you are converting mechanical to electrical and subsequently again converting into mechanical. Pump is a mechanical device. So, convert electricity, produce electricity by generator and use that electricity to drive the pump by motor, then that is not a good concept. So, therefore, because this pump itself is a bigger capacity, so instead of driving with an electrical motor, it is better to drive another turbine. So, this is the turbine which is used for driving a pump. Okay. So, that the mechanical to mechanical, direct mechanical to mechanical, so that your overall conversion efficiency is higher. So, these are parameters which are considered power efficiency, heat rejection in cooling, these are percentages for different this thing, and the losses, if you go for ultra supercritical, losses are minimal marginally, and heat rejected to the bottoming ash is this and considered as the same. Heat rejected through the stack, even ultra supercritical power plant is higher. Why? Because the heat the flue gases are going at higher temperatures. Okay. So, that is why heat rejection to stack is more in case of this, but the efficiency the power plant efficiency is higher than this. You see 35.9 to 42.3. So, the efficiency in case of ultra supercritical power plants by I think somewhere close to 7 percentage points. Generally here when you define the improvement efficiency, it is represented in terms of percentage points. There is a difference between percentage and percentage points. Okay. So, what is the difference between percentage and suppose if you look at what is the improvement in percentage when you go for ultra supercritical power plant of the efficiency, then what you do is this minus this by the this. Okay. Now 42, if you look at that, this minus this by initial one, like if you see percentage change in percentage is equal to 42.3 minus 35.9 or here. So, 42.3 minus 35.9 by 35.9, this is the meaning of that. What is the change in improvement percentage? So, if you look at that, it is about what is the difference, about 7 about 7 percentage difference. That 7 percentage relative to 35 is about how much 5 means about 20%. So, 20% improvement from this to this, 20% improvement is a substantial improvement, but actual improvement is percentage points is 37, you are it is about 6.4 I think. This 6.4 is the percentage point improvement, 6.4 is the percentage point improvement, whereas the efficiency improvement in absolute relative terms, it is about 20% improvement. So, that is but generally we go for percentage points rather than so, therefore, every 1 percentage point improvement will have a substantial impact on that. So, this is exergy balance is found here with the different power configurations, and with the different losses. Here efficiency, though energy efficiency is about 6.4 percentage points, whereas exergy efficiency is only how much, less than 6, about 5.8 here. From here to here is exergy efficiency is about 5.4. So, exergy efficiency is low because you are considering the quality of energy. So, loss in combustor, steam generator, through stack, turbine, losses condenser and cooling water, feed water heaters, losses through bottoming, bottom ash, and other losses are like this. So, this is a comparison. You can see that the conclusion here is useful work lost is higher in boiler as compared to the condenser, and so therefore, taking measures to reduce the losses in boiler is more advantageous than the compared to reducing the heat rejection at the condenser. So, therefore, it is important to come up with this, because where steam generator losses are very high as compared to in condenser, this one. So, based on this I will give you an example here. Consider a steam power plant operating on a simple Rankine cycle. Steam enters through turbine with this 3 megapascal and 350 degrees Celsius and condensed in a condensate pressure. Determine the irreversibility of the Rankine cycle, all 4 processes of the cycle. Assume that the heat transfer to the steam in the furnace is from 1325 degrees Celsius and the heat rejected cooling at this pressure. Determine the availability also of the steam leaving the turbine. Use these equations. This is the availability equation, and irreversibility is this. This is the irreversibility equation. We find out by using this. This is the availability equation. So, with this this I think this paper must have been already sent. Okay. 4E analysis, energy, exergy, environment, and economic analysis of solar thermal aided coal based power plant. So, which includes both solar thermal and coal based power plant, and apart from that other journals also you have papers you have to send. Go through them. If you do not understand, come to me, I will explain how it was done. These were published by our student. So, with this I close the topic of 4 exergy analysis of power cycle analysis. Then there is one more topic left. One more topic left. One more topic left, that is the last topic is what happened. Introduction to nuclear power reactors or power plants. Can you see this or we have to share it? Can you see the slides now?
Yes sir, now we can.
So, this is a topic 8 as far as the course is concerned, but topic 4 is as far as my part is concerned. So, nuclear so far we have discussed power plant cycle analysis, components, and then how do we deal this power plant cycle with respect to the second law analysis. That is what we have discussed. Now, the another topic is the nuclear power reactor. Nuclear power is important. Before that, I will give you some introduction to the nuclear power plant and current statistics. Maybe this is little low, it needs to be updated, but there is no much change, and there are several countries, more than 40-45 countries are producing substantial share of nuclear power, because nuclear is more environmental friendly, but of course, the other associated problems will also be there. US is the topmost with I think more than 100 reactors. France is next, China, Russia, South Korea and all these, and here is the nuclear India. So, it is a small fraction, it is about maximum of 3% of our total capacity, but there are several other countries. If you look at this, the China, France is the only country which uses more than 75% of their energy production from nuclear. You can see that this Ukraine is also another important country where they produce major share of their energy through nuclear. As far as the India is concerned, you look at that, this nuclear is only 3% of the total total energy installation, but it is even lower than that, because there are not many nuclear reactors are in either under construction or operational. So, therefore, you can look at this here. This is to be precise, it is 2.61% as compared to thermal, which is about 65%, more than 65%, but now renewables also gaining momentum. Renewable, this is by generation about 11%, but it is slightly higher in this case. Why nuclear? You perhaps you have studied in your basic physics, but still I will repeat some of the basic fundamentals of nuclear power generation. I do not know why this animation is not working here, but it is showing total entire content here, but nevertheless we will go one after the other. You know, fossil fuels, what we discussed earlier is coal based power plants. They are based on chemical energy, but nuclear same cycle can also be used by nuclear reactors. So, therefore, these reactions are either exothermic or endothermic reactions. For example, if a chemical form is this, if you carbon is converted into carbon dioxide, you will get 4 eV. 1 eV is given in terms of this electron volts. Chemical reactions of each atom participates as a whole and retains its identity. The molecules change, but the effect of this, the only effect is the sharing or exchanging the valency electrons. The nuclei are unchanged, unaffected as far as the chemical thing is concerned. In nuclear reaction, nuclei do not show up the products, either isotopes of the reactants or the nuclei are found in the nuclear reactions, and one of typical nuclear equation is this. So, here if you balance Z's as well as A's, here A is given, Z's are given here. So, although the mass numbers present in the nuclear reactions and mass of the isotopes on both the sides are of the equations do not balance, because there is a difference. So, here the nucleons and neutrons and protons are playing a role as far as the energy transformation is concerned. So, therefore, reactions resulting in change in mass, that is the delta M. Therefore, the release of large quantities of energy, that delta E according to Einstein law, this is E delta E is equal to delta m c square, and these numbers you know that the neutron and masses of neutron and protons and electrons are given here. This is missing, one electron is missing. So, therefore, the masses of the primary atoms are known, and that is the difference between nuclear reactions and chemical reactions. So, the cycle remains same as far as the coal based power plant power generation is concerned, but only the heat inputs are different, and a typical this is the Rankine cycle here, and the heat input is by nuclear reactor, and the rest is same, the cooling and others are same. And this is important here, how to generate heat to supply to the Rankine cycle is important, and it is made in of concrete, steel, and keeps radiation leakages, avoid radiation leakage. And the it is the simple one, fission to heat, steam, and then running turbine and electricity, and core of the reactor creates the heat. Nuclear reactor gives a small amount of mass, can give large amount of heat, and this is the difference between ITER. ITER is the fusion based. Now research is going on this fusion. The fission is this how they work. They basically, this fusion and fusion, the two or more lighter nuclei fuses into a heavier nuclei, that is one, and in fission heavy nuclei is split into two or more lighter nucleus. In both of these cases there is a decrease in mass resulting in exothermic reaction energy. So, that means energy is released. Those the reactions keep going on, that is a chain reaction, and there are only few fissionable isotopes, and these are some of the ones. U-35, India, as far as India is concerned, we are also working on 4th generation reactors like thorium based, like fast breeder reactors in Kalpakam. You have seen Kalpakam, there is a lot of activities going on there, and I think fast breeder reactor test bed is there in Kalpakam. But again, this actually closing the cycle is important. You have to close the cycle here. So, these are some of the fissionable by neutron for all energies, and these are fissionable by high energy neutrons only, because these are different isotopes and they are more U-235. Sometimes we convert from this U-238 to U-235. So, there is this thorium based and this plutonium based. This requires high energy neutrons, whereas the other ones are for all energies it will act. So, there is a difference between fissile and fertile materials. Fertile materials are materials that can undergo fusion, but will not sustain criticality, that is called fertile materials. And I think see here this down here, these fertile materials are these ones, the bottom ones. These are called fertile material, but requires which high energy neutrons. These are fissile material are that they can undergo fission and will also sustain the criticality. That means it continue to react and becomes a chain reaction. So, these are some of these isotopes. And here you can see it is a broad based nuclear reactors, how the nuclear reaction happens and what is the nuclear fission, and what is the difference between sustainable and unsustainable reactions. Nuclear fusion with U-235, if one neutron is bombarded with this, it is absorbed and becomes U-36 and then split into two other fragments, that krypton and boron, barium, and then it becomes a chain reaction. So, whereas here if you look at nuclear fission, this is a nuclear, it is a comprehensive approach here. You can see that nuclear fission in use, it goes nuclear reactions and it produces electricity here. By controlling it by a chain reaction, and it goes through moderator, and control rods are used for operating this. Apart from that, the energy which is comes out of this from uranium fuels, and then subsequently it U-235 to other fuels, and then there is a mass conservation, and then it is Einstein relations here and nuclear binding. This is a binding energy cause one side, the other side you have a fusion fragments. What happens after fission? So, uranium 235 forms from as a high excited isotopes with 2365 nucleon upon capture of these. So, you have seen that there are two neutrons also released while fission. One stray neutron hits, bombards to the U-235, then it becomes fragments, and then also two extra nucleons are produced. So, in order to reduce the neutron moments, you need a moderator and controllers. You have to control the speed as well as the moderation as far as the nuclear absorption is neutron absorption is concerned. So, here the U-235 and becomes U-236 once it is bombarded capturing one neutron, and this is unstable and breaks into variety of pairs of large atoms shortly after they are created. But many such, so there will be several such reactions. You can see here this is a generalized reaction, and the 203 mega electron volts are released. So, this immediate products, that means they are called prompt product of fission reaction, such as F1 and F2 are called fission fragments, and their decay products are called fission products, fission fragments and fission products. And if you look at energy from fusion and fuel burn up, then here you can see that U-235 when with slow neutron bombards, you will get these fragments, and apart from that extra neutrons are created here. And the reactions that participate in average reaction is this. There are different types of fragments, but you can see here this reaction yields 196 mega electric volts. So, that is a huge amount of energy. And another, there can be, I just now there need not, these fission fragments need not be the same, they can be different also, like this barium and krypton. And if you look at mass balance here in this case, 2 neutrons extra produced. So, in what happens is this, if you open it, it will be a chain reaction and indefinitely grow large number of neutrons. So, therefore, it needs to be this one. So, therefore, how do we get this 193 here just now 196, that 196 is here if you add all those things. So, the average fission of U-235 nuclei yields about 193 MeV, and this amount of energy is the prompt, and that means it is released at the time of fission. So, here these are the percentages of different, if you the fission of U-235 releases into this kind of things. Fragment kinetic energy is this, kinetic energy from fission neutrons, and then energy of prompt gamma, then beta, gamma, neutrino, all these are released from this with the different energy levels here. So, therefore, it is important that the energy produced because of slow decay of fission fragments into fission products, fragments are converted into products, and the non fission capture of excess neutrons in reactions that produce energy. So, therefore, the total energy produced per fission reaction it is greater than that of the prompt energy. That means, at the time of release energy is much lower than the total energy which you combine all of these things. So, fuel burn up is the complete fission of 1 gram of uranium U-235 nuclei is I think some part is gone, here is 0.948 megawatts per day. So much energy, only 1 gram produces so much energy. So, that is why nuclear energy is important, and radioactivity is another important characteristics, and radioactive radioactive isotopes continuously undergo spontaneous and disintegration, usually emission of one or more smaller particles from the parent nucleus and change into another or daughter nucleus. There are several successive decays and occurs until the stable isotope is formed, because once uranium 35 it forms into different fragments and then ultimately transformed into fission products, and each of one of these give you different this thing, and there are isotopes which are emitted alpha, beta, gamma particles or radiations. Here see there are thermal neutrons, I will explain you what is thermal neutrons and so on. The fission neutrons are scattered and are slowed down by the materials in the core of a reactor, and the reducing the speed or scattering and slow downing the neutrons called moderator. This is a scattering medium. Once the nucleon goes into that, they become slow. So, that is called scattering medium, it is called moderator, and this is a moderator is required. So, here if you look at this, we have to, in order to sustain the reaction, suppose if you release some neutron, at the end of the reaction you have to keep same number. For example, if 100 neutrons are slow neutrons are absorbed by the uranium U-235, then at the end of reactions also same 100 should be there. So, therefore, this moderator and control are important here, controlling the process is important. Here I will explain you this table, this schematic later. Before that, there is a small nuclei with high neutron scattering. Means if neutron goes and scatters into the material here, neutron absorption, low neutron absorption probability. What happens is these neutrons go into the material and become slower down, that is called moderator. So, generally hydrogen H atom and D, H and D, H2O and D2O, that is a heavy water, D2O is a heavy water, HD, graphite, barium and barium oxides are also used as a moderators, but some of cases, most of the cases, these D2O heavy water, in heavy water reactors, the heavy water is used as a moderator for the thermal neutrons. See, the low energy they reach are those that they put them into thermal equilibrium with molecules of medium and medium they are in. So, therefore, it is these neutrons they become thermalized and called thermal neutrons. This is a special category of slow neutrons. Here you look at these, there are 100 fast neutrons left, and then 2 immediate fast fissions formed here, and with that there will be, it becomes 103 because of 2 immediate fast, because when it releases, see one reactor, suppose if you go one slow reactor with absorbed by U-235, it produces 2, and then one of them is used to produce another 2. So, total 1 plus 2 3, that becomes 103 for 2 immediate fast reactions. And here this 103 10 fast neutrons are absorbed or leaked from the core goes into this, and then you will get 93 thermal neutrons, which we here you mentioned they are thermalized because of this medium. So, that becomes 93 thermal neutrons, and then out of that 3 thermal neutrons escape from the core, and 90 absorbed at the thermal energies, and out of which 43 absorbed while diffusing at the thermal energy, this one, and 47 absorbed in fissionable material, and out of 47, 7 are lost in non fission captures, and the remaining 40 goes to fusions. Then ultimately you will get again 40 into that 2 points something will get again 100 neutrons here. So, you see that in the process you can see the 63 neutrons out of 103 goes into that, and 40 are responsible for sustaining the reactor reactions. So, fission reactors, where there are various types of fission reactors, and mainly U-235 is the fuel which is operated at steady rate. More than 1.47 neutrons should be lost to the fusion process, because we said 2, but average number is important here. So, there are several losses occurs, mainly in 2 ways: non-fusion absorption in a reactor, because you have seen this absorption here, this part is important here. So, which includes structural material, coolant, channel, walls, fuel cladding, coolant, moderator, and fuel materials itself are the responsible, and leakage through core also another important thing, and this is mainly both for core materials and size. See, in nuclear reactors we have seen as a concrete dome is covered with the entire this. Sometimes these more leakages can also happen if there is a neutron mean free path in the core material is larger than that of the reactor size is smaller, and it is important to have surface volume ratios large. And here the fusion reaction types is actually their obtained criticality or study power in 3 methods. One is building a heterogeneous reactor and enriching the fuel, or even combination of these. So, reactor components are fuel rods, that in which the fusion occurs and heat is generated, and moderator is to reduce the energy of the neutron, and coolant is to remove the heat from the fuel element. That is a coolant is used to supply the heat to the Rankine cycle. So, this is the typical process here. So, how the coolant is circulated, how the control rods are placed, and how the moderator is used. This is a moderator. So, you see that if there is a nuclear reaction from the previous generation, the fusion occurs and the heat is absorbed by the coolant, and then the rest of the neutron speed is controlled by the moderator, and then you have a control rods which reduces the activity of the nuclear reaction, and then this follows the same. See, one of the nuclear these neutrons are leaked through outside, only the extent that to sustain the chain reaction another neutron, and this part is same as another part here. So, this is a repetition of that. Then if you look at the reactor components, fuel rods are there, and moderator. What is a fuel rod? Is again enriched uranium, that is U-235. The fuel rods are selected based on what availability and high cross sectional section for fission and sustaining a chain reaction. So, naturally occurred uranium contains about 99.2% of U-238, only 0.71% of U-235, but U-235 has a high cross sectional area. So, therefore, this is enriched to convert enriched, that means this U-238 is converted into U-235 because it has a high cross sectional area. The moderator side, let me complete this uranium fuel here. Natural uranium composed of this 0.7, I have already mentioned 0.72% U-235, that is a fissionable isotope, and major fraction is U-238, and of course, some traces here of 234. And this is not sufficient to produce self sustaining critical chain reaction. So, for mainly for light water reactor, light water means normal water H2O, the fuel must be enriched 2 to 3% of this. So, this 97% of 99.2% of this should be enriched with to enrich to get to 2.25 to 3% this. So, fuel pellet is like that, and they put into fuel rods, and then they convert into full fuel assembly. This is about fuel side, and the moderator is it is mainly to slow down the fission neutrons, and good moderator should have following property: low absorption, cross section, and high scattering cross section, smaller nuclear mass, good chemical properties, and heavy water is used and ordinary waters are suitable for moderators. This is the how heavy water is used to as a moderator here you can see in this reaction. So, the slow two neutrons are bombarded and then in a U-235 nuclei and they form into different fission fragments, and then you will get fast, some cases 2 neutrons extra, then some cases 3 neutrons, average is somewhere 1.47 neutrons, and then they go into the moderator and absorbed, and then finally you will get only same 2 should come out as a 2 for sustaining the chain reaction. So, with this I will end today as class, and in the next class we will discuss more on this complete different reactors and how they are used in this, and major issue with the nuclear reactor is spent fuel, how to manage spent fuel, and also how to make use of decommission. See, suppose decommissioning is a major issue after end of the life. Every nuclear reactor has certain life, but after end of the life what we have to do, and that is why nuclear accidents, because of that I think across the world the nuclear energy is going down, and some countries they are phasing out the nuclear energy. So, we will discuss that later in full detail. Thank you.